So in the previous class, we have seen some examples of embedded systems in the application specific and domain specific. We have seen the example of washing machine in application specific embedded system and automotive domain in domain specific embedded systems. Today, we will see the next topic, that is hardware, software, co-design and program modeling. So when we see an embedded system, we know that we have both hardware and software embedded together. So while we say of designing an embedded system, we're actually designing hardware and software, both of them. So how we design the both hardware and software, we are actually going to design them together. That's why it's called hardware software co-design. So in traditional embedded system development approach, hardware software partitioning is done at an early stage. That means initially itself the hardware and software are partitioned. So what do you mean by hardware software partitioning is that, so when we want to achieve some function, so we can do that by using a software and by using a hardware. Okay, so when we say an embedded system, we have both hardware and software, and some functions have to be done by hardware and some have to be done by software. So the partitioning of which have to be done by hardware and which have to be done by software, that is called hardware software partitioning. So in traditional approach of embedded system development, this partitioning of hardware and software is done initially or at an early stage. So the engineers from software group, they take care of the software architecture development and implementation, whereas engineers from hardware group, they are responsible for building the hardware required for the product. Okay, the software engineers, they develop the software part, the hardware engineers, they develop the hardware part, and there is no or less interaction between the two teams, and the development happens either serially or in parallel. Serially means one after the other. First hardware will be designed, then software, or vice versa. Parallel means together they will be doing, but there will be no proper interaction between them. That's the traditional approach. Okay, once the hardware and software are ready, the integration is performed. That means they are put together once both are ready. But the increasing competition in the commercial market and the need for reduced time to market, that means products have to be brought to the market in a lesser time, the moment they are conceptualized, they have to be brought into the market in as less time as possible. Okay, because of that, the product calls for a novel approach for embedded system design. So some different approach has to be used rather than this traditional method where the hardware and software are designed separately or independently. So in this new approach, the hardware and software are co-developed instead of independently developing both. Co-developments, they are developed together. Okay. So during the co-design process, the product requirements captured from the customer, that means the requirements from the customer, they are taken and they are converted into some system level needs or processing requirements. So these processing requirements, they will not be partitioned. They will not be partitioned at this particular time. At this point of time, it is not segregated or partitioned as either hardware requirement or software requirement. Instead, it is specified as functional requirement. It will just be taken as functional requirement, like what function has to be performed based on the customer requirements. The system level processing requirements are then transferred into functions which can be simulated and verified against performance and functionality. This is the system level design. So after the system level design, there is an architecture design. The architecture design follows the system design. So during this architecture design phase, the partition of system level processing requirements takes place between hardware and software requirements. Some functions can be done using hardware and some can be done using software. So that partitioning is done during the architecture design. So each system level processing requirement is mapped either as hardware or as software, or sometimes both. Okay, some components may be requiring both hardware and software requirements. The partitioning is performed based on the hardware software trade-offs. So there are certain trade-offs, like suppose you want to perform certain tasks using hardware, then the cost might increase because you might have to use an extra hardware. Suppose there are some complex calculations like some DSP operations you have to perform, you can use a DSP for that, digital signal processor, to perform that, but the cost will increase, right? So if you want to go for parallel processing, okay, you might have to use some additional hardware for that, so the cost will increase. But what happens is the processing time will decrease. So for the DSP function, if you want to implement it using software, you will have to write more lines of code, right? So there is a certain trade-off. If you want to reduce the lines of code, or if you want to increase the speed, you will have to be ready to spend little more. If you cannot spend more, then you will have to be ready for lesser speed or lesser performance. So those are called trade-offs. If you go for one advantage, you will be having another disadvantage. So you have to decide on what is your priority. Depending on your priority, you will have to select the most advantageous thing for you. So the architectural design results in detailed behavioral description of the hardware requirement. You know what a behavioral description is after you have studied the hardware description language, right? And the definition of the software required for the hardware. So it gives a behavioral description of the hardware requirement and also what software is required for the hardware. The processing requirement behavior is usually captured using some computational models. So what is a model? So we are going to see that the models representing the software processing requirements are translated into firmware implementation using programming languages. So before we write a program, first a model is developed, then based on that model, some programming language is selected and program is written. Okay, so there are certain issues or fundamental issues in hardware software co-design. So four issues we can make a note. That is selecting the model, selecting the architecture, selecting the language, and partitioning the system requirements into hardware and software. So these are the fundamental issues in hardware software co-design. So we will go through these one by one. The first one is selecting the model. So which model to select and what are the different models available? So in hardware software co-design, models are used for capturing and describing the system characteristics. Capturing means to get it, I mean, to from the customer requirements or the market needs. We first have to note down what are the requirements, right? And then they have to be described. The characteristics have to be described. So it is a formal system consisting of objects and composition rules, certain objects and some rules. So it is actually hard to make a decision on which model should be followed in a particular system design. So most of the designers, what they do is they switch between different models depending on the need or requirement or depending on what stage the product is in. Okay, so the objective varies with each phase. For example, if it is at the specification stage, that means initial stage, only the functionality of the system is in focus. So we do not know how it is implemented. We know only how it is supposed to be functioning. At that time, we might be going for one model. But when the design moves to the implementation aspect, when it is ready for implementation, more of the information is available. The information about the system components is revealed. So designer can switch to a model which is capable of capturing the system's structure or architecture. Okay, so that way, depending on the stage of or phase of which the product is in, the models can vary, and it is actually a difficult task to decide or select a particular model. So we will have a look at different models in the upcoming topics. So next issue or next fundamental issue in hardware software co-design is selecting the architecture. The model is not the complete architecture. It is just a model, like what are the things. So it doesn't give the implementation part. A model only captures the system characteristics and does not provide information on how the system can be manufactured. Okay, whereas the architecture, it specifies how a system is going to implement in terms of number and type of different components and the interconnection among them. So the actual implementation thing requires what architecture you select. So commonly used architectures in system design are, there are different architectures like controller architecture with the help by using some controller, a data path architecture. You have seen this in, if you remember, you have seen this in computer organization, the last module, right? Single bus and multiple bus, those things. So data path architecture. Then CISC and RISC, complex instruction set computing or reduced instruction set computing architecture. Very long instruction word computing, that is VLIW architecture, where the parallel execution of instructions can take place. And these are parallel processing architectures actually, SIMD and MIMD, single instruction multiple data and multiple instruction multiple data architectures, where single instruction can operate on or can apply to multiple data at the same time, or multiple instructions can operate on multiple data at the same time. So that those are parallel processing architectures. So some of them, they can fall into application specific architecture like controller architecture, while others fall into general purpose architecture like CISC or RISC, or parallel processing like VLIW, Verilog instruction word, single instruction multiple data, SIMD and MIMD. Okay, so we will see each of them. The controller architecture, it implements the finite state machine model. So this is one of the models that we are going to see again. FSM model we call it, or finite state machine model. So might have studied this finite state machine in your digital system design, right? The Murray model, Mealy model, and all. So using a state register and two combinational circuits. Okay, so it's a basic one. State register and combinational circuits you can use. The state register holds the present state, and the combinational circuits implement the logic for next state and the output. So state register means it's like you're having a control word or the state register. Then there will be some implementation logic, I mean the logic circuit or combinational logic circuit, one for the next state and one for the output. Then the next one is the data path architecture. It is suited when you are using, when you are following a data flow graph model. That is one of the models again, where the output is generated as a result of a set of predefined computations on the input data. So it is, you perform some predefined calculations, you take some input, perform some operation, get the output. In such cases where path is defined, that is called data path, and for such things you can use data path architecture. So it represents a channel between the input and output. Data path is actually a channel between input and output, and this data path, it can contain registers, counters, register files, memories, and ports, along with high speed arithmetic units. The ports connect the data path to multiple buses. So most of the time arithmetic units are connected in parallel for support for parallel operation or pipelining, which can increase the speed and bring high performance. So arithmetic units, they are connected in parallel. That is about data path architecture. Next, the finite state machine data path architecture. This is one of the types of data path architecture which combines both the controller architecture and data path architecture. Controller architecture is for FSM model. Data path architecture is for data flow graph model. So if you take a combination of this, we call it FSMD, that is finite state machine data path architecture. It combines both the controller architecture and data path architecture. So it implements a controller with data path. Okay, there will be both controller as well as data path. The controller generates control input, whereas the data path, it is used for performing the operations on the data, that is for processing the data. The data path, it contains two types of IO ports, out of which one acts as the control port for receiving or sending the control signals from or to the controller unit, and the second IO port interfaces the data path with external world. Okay, one is for receiving or sending the control signals from or to the controller, that means in both the directions. Okay, and the second IO port interfaces the data path with the external world for data input and data output. Then normally the data path is implemented in a chip. That means it will be inbuilt in a single chip, and the IO pins of the chip, they act as data IO ports for the chip resident data path. So some pins of the data, some pins of the chip, they will be the IO ports for the data path. Next, RISC and CISC, what this means already. CISC, or complex instruction set computing, it uses an instruction set representing complex operations. Okay, so instructions in CISC, they are complex in nature and they are also more in number. So it is possible for a CISC instruction set to perform a large complex operation with a single instruction. So I had given you an example while considering this in the first module or the third module, that is a CJNE instruction or a DJNZ instruction, right? Which is actually a combination of three or four functions actually. So reading a register value, comparing it with the given value, and then transfer the program execution to a new address location. This is done by using a CJNE instruction in 8051 architecture. So it will compare two particular values. Okay, if it is not equal, it will jump to a particular location. So that is the thing. So the use of a single complex instruction in place of multiple simple instructions greatly reduces the program memory access and program memory size requirement. So if you use multiple instructions for the same task, the lines of code will be more. So it will take more size of program memory. Whereas if you use a complex instruction, you might require a complex instruction decoder, but it will take a lesser program memory size. So it requires additional silicon for implementing microcode decoder for decoding CISC instructions. So additional hardware is required for this. The data path for the CISC processor is complex. Okay. If you consider RISC, it uses reduced and simple instructions. So it requires execution of multiple RISC instructions to perform a complex operation. Suppose you want to perform the complex operation in CISC, you can do it with a single instruction maybe. But if it is a RISC architecture, then more number of instructions are required to perform the same operation comparatively. So the data path of RISC, it is actually simpler compared to the data path of RISC. It contains a large register file for storing the operands and output. It is designed to operate on registers, and RISC architecture supports extensive pipelining. Okay, it supports pipelining. Next kind of architecture is VLIW. As we have seen, VLIW is very long instruction word architecture. So this implements multiple functional units, that is ALUs or multipliers, etc., in the data path. So there are more than one ALUs. If there are more than one ALU or one functional units like multipliers, adders, and other things in a single data path. Okay, so that means it allows for execution of uh, the instruction more than once at the same time, parallel execution of instructions. It's called parallel execution of instruction. So what happens is, normally the instruction will be written in, there will be an instruction cache memory present, where the instructions or different independent instructions are put in the instruction cache, and they will be executed parallelly. Different instructions can be executed parallelly at the same time. So the VLIW instruction, it packages one standard instruction per functional unit of data path. So all these VLIW and including SIMD and MIMD, they are for parallel processing. The parallel processing architecture implements multiple concurrent processing elements. Concurrent means which are processing at the same time. Okay, and each processing element, or PE if you call them in short, they may associate a data path containing register and local memory. So there are two types again, SIMD and MIMD, that is single instruction multiple data and multiple instruction multiple data, which are examples for parallel processing architecture. In SIMD, that is single instruction multiple data, a single instruction is executed in parallel. That means a single instruction is executed parallelly on multiple data. So you might be thinking how single instruction can be parallel. So parallelly, the same instruction will be operating on multiple data, okay, with the help of processing elements. The scheduling of the instruction execution and controlling of each processing element is performed through a single controller. There will be a single controller in this. The SIMD architecture, it forms the basis of reconfigurable processor. Okay, that's a different concept of reconfigurable processor, for which this SIMD architecture is the basis. Next type is MIMD. Here the processing elements execute different instructions on different data or multiple data at a given point of time. Okay, so this forms the basis for multi-processor systems. Okay, then comes multi-core processor systems. So these are all parallel processing themes. The processing elements in a multiprocessor system communicates through mechanism like shared memory and message passing. These are different mechanisms for sharing the messages, okay, which we are going to see in the fifth module, the shared memory, message passing, and other things. So these are the two things we have seen, that is selecting the model, selecting the architecture, then we have to select the language. So this comes in the software part actually. So we have to select the language. A programming language captures a computational model and maps it into the architecture. Okay, so it is actually a link between the computational model and the architecture. So there is no hard and fast rule to specify this language should be used for capturing this model. So nothing like that. Like for this particular model, this language has to be used. There are no rules like that. Depending on what is suitable, a programmer or the designer can choose any language. A model can be captured using multiple programming languages like C, C++, C Sharp, Java, or any other thing. For software implementation, okay, you can use Python also, and languages like VHDL, System C, or Embedded C, or Verilog, right? Or for hardware implementation, you can study these hardware description languages, Verilog, HDL. On the other hand, a single language can be used for capturing a variety of models. Certain languages are good in capturing certain computational model. For example, if it's an object-oriented model, there is one model called object-oriented model. Then you have to use object-oriented language like C++ or Java. Okay, so the only prerequisite is selecting a programming language for capturing a model is that the language should capture the model very easily. That's all. If it captures the model very easily, that means the model can be interpreted using that particular language easily, then that language is suitable for that particular model. That is what we have to be careful. The last fundamental issue in hardware software co-design is partitioning the system requirements into hardware and software. So, from an implementation perspective, it may be possible to implement the system requirements in either hardware or software. That means firmware. So we have seen this. It is a tough decision, like which one has to be done using hardware and which one has to be done using software, right? Because as I said, there are certain trade-offs. If you go for hardware implementation, you might have to spend more bucks. If you want to go for software implementation, you might have to give up on your desire for high speed, because for software implementation it might take more time or more memory to store the program uh, in the program memory, right? So various hardware software trade-offs are used for making a decision on hardware software partitioning. So depending on your priority, you can choose what things you want to implement using hardware and what things using software. So these are the fundamental issues, that is selecting the model, selecting the architecture, selecting the language, and partitioning system requirements into hardware and software. So next we have computational models, different computational models we use in embedded system design. There are some 6 models that we are going to study: data flow graph model or DFG, control data flow graph model, state machine model, sequential program model, concurrent or communicating process model, and object oriented model. Okay, so we will see each one of these one by one. I will continue that in the next class.